Hi everyone, in this video I'd like to review this problem of computing the exact value of the area of a triangle. There is a formula known as the Heron's formula. So that's its name, Heron's formula. If you plug it into this formula, the answers can be straightforward and easy, but that's not the point of doing this exercise. And through this exercise, we have an opportunity to link these different laws and formulas together to understand how this Heron's formula actually proved. So that's the purpose of it. So in here we're not actually using Heron's formula, but use other formula to using this example we understand what how we actually got this formula. So namely, the first one is the area formula that uses a sine theta. That's the one thing. And the second would be the law of cosine. Mainly using these two formulas that we studied recently, then we can compute the area of this triangle, for which we don't have any angles given, but all three sides are given here. So the solution goes like this. I'm going to sketch the triangle again one more time in 3 and 4 and 6. Here's the triangle again, but to use this area formula, we need an angle. So you can choose any of this angle. So the method we're going to do will work with that angle. But since the angle is down here, I think is more oriented. We've been seeing this angle located in the left to lower corner like this. So I'm going to call that angle theta right there. So our area A is half times two adjacent side of this angle relative 3 and 4. Here's a 3 and 4. And this sine theta, and that was the area formula that I was talking about. So let me go ahead and underline this part again, exact value. So everything is exact, and if you're not turning this result into a decimal expansion, that would be an exact value. So here we're keeping this form, so that's exactly 6. So let me go ahead and simplify this 2 and 4, makes this 2 here, just 6 times the sine theta is the value. To find the exact value, we need to keep the sine theta in the exact way. Okay, not using sine inverse or anything to get it turned into a decimal expansion. So that's the goal of this problem. So the law of sine, to move a little bit, law of sine requires knowing some of the angles here, but law of cosine pretty much requires only one angle. So since we know all sides, the cosine theta can be computed exactly if we have 3 sides in here. So let me write down the law of cosine. Law of cosine can be stated for any angle in here, but if you're looking at this angle right here, we have 2 adjacent side and opposite side relative location of these 3 sides to the angle theta, and we have a Pythagorean theorem-like statement. So here's the opposite side, 6 squared. And here's the 2 adjacent side, 3 squared and 4 squared. So up to here looks like a Pythagorean theorem because it's not a 90 degree here. We must have this adjusting factor. That's how I introduce this law of cosine. And we don't have to state other versions. This is the one part that we're going to use, the law of cosines here. And what we want to figure out is a cosine theta. So in class, I also introduced this, how this one, the cosine theta is isolated. So let's go over that part. And this is a big quotient. Down there is a 2 times the product of 2 adjacent. So it's a 3 and 4 there. And the numerator is this, the square part shows up. So the sum of the square of the 2 adjacent sides shows up first, and 6 squared later. So if you isolate this part right here for the cosine theta, you will always end up at this part. Remember, the denominator is a 2 times 2 product of the adjacent sides, and the numerator kind of comes in this order. So we have to calculate this one exactly and not turning into a decimal expansion. So it turns out it's negative 11 over 24. Right? If you simplify and cancel the common factors, and that's actually there's no common factor to cancel, this denominator is exactly 24. So that's what cosine theta value is here. Remember, what we want from the cosine theta value is what is the sine theta value, right? So if we know the sine theta value, you can just plug it in here and we get the answer directly. So let's think about how this cosine theta and sine theta is related. And also I wrote that before we enter that, remember this theta is an angle in the triangle, so we do have this range in 0 to 180 degree. For that, sine theta value is always a positive or 0. Because in the first and the second quadrant, sine theta value was a positive value. You see, as this theta varies from 0 to 180 degree, as this triangle suggested, it seems like an obtuse triangle, and then you're verifying here negative 11 over 24. Negative cosine theta happens when theta is greater than 90 degrees. So we know from there more than just 0 to 180 degree, but I put this range for general case. If it is not an obtuse triangle, you will have positive number, and this inequality for all cases is always true. So what we want is a sine theta value from this cosine value there. So there are many different ways. The most straightforward way of the fastest way of doing this is using the Pythagorean identity. So here's the Pythagorean identity. It's called, it looks like this, sine squared of, here we're looking at the theta. Doesn't matter what the theta is, as long as you have the same angle for sine part and theta part, cosine part, it always ends up in 1. Doesn't matter what theta is. You can experiment this with a calculator, and you probably proved that in class. So using that, if you know the cosine part, you can compute the sine part in here. So let's isolate it. Here's a sine squared theta. It's 1 minus cosine squared theta. Right? And we know what cosine theta is. Think about the meaning of this one, and this is what it really means. It's the abbreviation of whole quantity cosine theta squared. That's the this is what this shorthand is for. It's 1 minus. We found that was 11 over negative 24 with a negative, and then negative 11 over 24. This whole thing is squared. So that square will change that negative here to a positive number. So let's do this arithmetic. Alright, it turns out sine squared theta must be this 455 divided by 576. So here's the part you have to be careful. We are solving for sine theta, knowing that sine theta is going to be a positive number because theta was in between 0 and 180 degree before. So here we're not turning this one again into decimal number, but we're just keeping this square root symbol here like this, 455 divided by square root of 576. Okay, that's what sine theta value is. Now we figured out in exact form, what the value of sine theta is. Let me go ahead and show you what the area was. So here's the beginning part of the solution. We wrote down the area here to be 6 times the sine theta. Okay, so that's why we detoured and evaluated the cosine and everything. So let me copy that down. Area A that we're looking for is a 6 times the sine theta before. Now we know sine theta in that form, so it's a 6 times root 455 and square root of 576. So that number is the exact area of square root of A. So in this exact form, we can calculate with assurance that, if you want to decimal places down to 10 places or something like that, you can calculate it exactly. So that's the answer, exact value of the area of the triangle with the size 3, 4, 6 there. All right. Just for fun, at the end that I'm gonna turn this one into a decimal answer. So seems like the area down to a few more digits here is this value here. But what was asked is exact value. Thank you.